all of our homework is due by when?
It would be December 9th on Monday.
Okay.
Yeah.
I knew it was before like the actual end of the semester, so I wanted to make sure that.
Well, welcome back, everyone. It's like we have to run the clock, but almost there. Well, it's official. Looks like we can start. Welcome back, everyone. I hope it was a restful holiday. And now this is a great place to be in. It's week 15 out of a 16-week semester. So in a real sense, this is like the last week. Next week, all we're doing is the final exam. And this is the last bit of material for the entire class. There'll be exactly one problem from section 5.4 on the real final exam. So our goal is just to hit the section 5.4 notes. We have 2 examples in there. And then when we come back on Wednesday and Thursday's class, all we're doing is reviewing for the final exam. We go down through the list of the announcements. We don't have any quizzes that are due this week, but there is, let me take a look, an extra credit quiz. This one's due on the day of the final exam, and it goes beyond the course material. So if you open this up and you decide, I don't want to do this, that's completely fine and reasonable. It's not too big of a deal as far as the extra credit. But if you look at it really carefully, you'll start to notice a lot of this is pretty familiar. You know how to calculate p-hat. You just have to calculate it for 2 different samples. Standard error is different, but you work through the formula just like you've done other things. And it goes just kind of the same way. So if you decide to get through this problem, the major punchline about it is doing an introductory class in statistics, you don't learn a lot of procedures, but you start to find out that if you look into the other procedures, they really aren't too different from what you've already done in this course. So that's the kind of big takeaway with this quiz right here. This is totally new material, but if you walk through it carefully, it could feel a lot like quiz 8 or 9, for example. Aside from that, there's another extra credit opportunity. This one is for the course evaluation, and I think about half the classes completed it. But I just wanted to mention it does have a final due date December 6th. So I'll probably just mass email the whole class and let people know one last time to be sure to complete it before the due date. Aside from that, the final extra credit opportunity is relative to the final exam. If your final exam grade is higher than your minimum grade amongst exams 1, 2, and 3, it will just full out replace that minimum grade. So if you had a bad exam, then this is a great way to replace that. And aside from that, I think I'm running out of announcements, but questions so far?
So if our final grade is like higher than our exam 2, then it would just replace that grade 2?
Only the minimum. So let's say for a really quick example, maybe let's say exam 1 came out to 83, exam 2 came out to 81, and exam 3 came out to 79. If this hypothetical student had a final exam grade that came out to let's say it's a good color for that, let's go with purple. Let's make it be maybe 85. And that new grade of 85 comes right here, kills that one, places that at 85, but it leaves the other 2 unchanged in that case. So only replace the minimum score.
Okay.
Other questions about that so far? Okay. Other extra credit opportunities are pretty much any quiz that has gone past due, whether it's all the way at the very, very top, say, if you missed this one, then I do accept these for full credit. And it's a great way to study for the final exam. In fact, one final exam sample is this one, version 3. If you open up sample at final exam version 3, you'll notice these are literally just the quizzes. This is my way to say that these quizzes really were important kind of information. For example, go to the very bottom. I think I've asked this question as a real exam question in the past on the final exam. And same for probably this one as well. No, maybe not this one. I think this gets used as a quiz over and over again, but that's the kind of idea. These quizzes are meant to be legitimate exam questions, even with the formatting. So you can come back there, complete any quizzes that are missing, and I'll accept them for full credit. The only firm due date is everything has to be due on Monday, December 9th. This is officially the last day of the course, essentially. Aside from that, there's other sample final exams. Version 1 is the same one that we've been doing all along. It just extends all the way now down to the new content in chapter, okay, keeps on going and going. Forget how long these get. It gets into chapter 15 in hypothesis testing all the way down for section 15.4. So this is the same exact problems that have been posted under exams 1, 2, and 3, but now that's the full set. So there's that document. Version 2 is all of the lecture notes. What happens with the lecture notes here in version 2 is you go to a random section, say way down here, for example, way down here, go to a random section like say 13.3. What I did is I took the real 13.3 notes, the same ones that we went through. I deleted all the formulas, all of the extraneous stuff, and left just the actual examples. This one starts at example 2 to say in 13.3, example 2 is a legitimate exam question that you could rehash and go through again. And you can check your work pretty rapidly. Just note the section title, 13.3. Moodle webpage is now a gigantic resource, so you can just go here, find the solution down in example 2. There it is, and you can work it simultaneously, checking the solution as you go to see if you've missed anything along the way. So that's our second version of the final exam. Third version is, again, the blanked out quizzes. But I didn't call this a sample final exam, really, because it doesn't include everything. It ends right at exam 3. But another great way to study for the final exam is open this up, grab either one of these exams. I would say take a look at your old exams, and the one with the minimum score, that's probably the best one to start looking to practice. If it was, say, exam 2 for just a random example, this is the actual exam 2, but everything's been blanked out. So you can redo it again at your leisure, maybe even time yourself at 75 minutes to see how you're doing with a time constraint. And like before, you can check your work by going to the right spot on the Moodle webpage. That would be exam 2. And solutions are posted right below the exam information. So that's all down here for self-study. I'm going to leave all these documents pretty much just for you for studying. So when we come back on Wednesday's class, I'll post a new document right here between the section and, or right here rather, between section 5.4 and all the other stuff. It'll be called Final Exam Review Questions, and it'll be new problems that we'll go through on a problem by problem basis. But if there's anything down here you want to revisit, take another look at, don't hesitate to ask. I'll be happy to drag those out and we'll solve any questions that come up as well. That's a lot of announcements for today, but any questions at the moment?
For the next 2 days, we'll just be going over.
Yes, correct.
That stuff.
Yeah, if we don't quite finish out 15.4, that's what we'll start on Wednesday, but then directly going into reviewing, absolutely. Any other questions at the moment? Okay, and maybe last bit of the announcements.
So the sample version 1.
Yeah.
That's all the chapters, right?
It's everything all the way down to 15.4, yeah. Some of them are old stuff we've already rehashed before, but it's now there in all one big set. Another thing I want to mention, and I think I need to kind of highlight this a little bit better because I missed it too. One last announcement is the really astute reader might have noticed this. There's been one small change on the exam for the final exam, and it's right here. Because there's so much information on the final exam, instead of the 1 page of notes, I bumped this up to 2 pages of notes, front and back. So let's see how to actually really highlight that.
And are we taking it in class?
It'd be in class, yeah. Okay. It'll be in this classroom, 5:30 on Monday, yeah. So this will be bumped up to 2 pages of that size. I think red is a good way to kind of, how do you get red going? There it goes. Okay, so we'll probably rehash a couple of these things once we get on our Wednesday review and Thursday review. But so far, that's pretty much the plan for the rest of this week, all the way into Monday, December 9th, our day of our final. Any other questions at the moment before we get started? Okay, well, let's jump in. We're in section 15.4. And with all good sections in statistics, it starts off with the central limit theorem. This one is the central limit theorem for means, and it was pretty much just copy pasted out from chapter 14 when we did the confidence interval procedure for a mean. So just to run through it, the big content of this central limit theorem is right here where they say your sample mean can be well approximated by a normal distribution, even when the underlying population is not normally distributed. The more skewed your underlying population, the larger your sample size n has to be to make the statement true. But that's the magic of the central limit theorem. Even if your population is horrendously skewed, the moment you grab a sample size of size n, calculate your sample mean y bar, this statement is saying now y bar came from a legitimate normal distribution, or it's very well approximated by one. And that approximation only gets better and better as the sample size n gets larger and larger. This enabled us to do confidence intervals, and now it's going to enable us to do hypothesis testing next. So pretty much here's how it goes. If we're going to use this theorem, we have a big problem right here. The trouble is both mu, this is the mean of the population, and sigma, this is the standard deviation of the entire population, are unknown. We can estimate them, but what we would like to do rather is the following. Calculate a standard error for this quantity right here. So here's our quick example dealing with that kind of issue. And I think we've seen these data before, so it's just a really fast problem on example 1. It says the Federal Bureau of Investigation compiles data on robbery and property crimes, publishes the information at population at risks, rates, and selected crime indicators. So you can Google that to take a look at data if you like. We're told we have a simple random sample of 25 pickpocket offenses. Yeah, I think we did a confidence interval problem on this one. So this is telling us the sample size n is 25. It yielded a sample mean loss of $513.32. So the moment we see that, we should write down y bar is 513.32. And it goes on to say next, sample standard deviation loss of $262.23. So that's S now at 262.23. So that's our run through on the problem. Now, first thing it asks us to do is calculate the standard error of the sample mean. And this is pretty much a review question because when we were a long time ago, it feels like, doing confidence intervals, we needed that standard error. So the review on that is, here's what it would look like. We write it SE for standard error. Because it's for the sample mean, we write it of y bar, where the parentheses are literally just saying of. And the formula is attempting to copy this right up above here, the sigma divided by root n. We run into this constantly. We don't know mu, we don't know sigma, yet sigma is approximately equal to exactly the sample standard deviation S. So that's the idea with the standard error. We throw in S right here. We divide by the square root of the sample size, so square root of 25. That's an S in the numerator. Let me see if I can fix that. So all we're trying to do is approximate this thing right up here. That's why it's called the standard error. Just a reminder that we're making an approximation. So next steps, throw in S at 262.23. Divide by the square root of 25, or just 5 if you simplified your root. So this will be the calculator step of this problem. So 262.23 divide by square root of 25, easier to just punch in a 5, save some calculator steps. And we get this as a standard error, 52.46446. We did it, folks. That's our standard error in the problem. Again, it's kind of a review, but it's been such a long time since we've done this confidence interval that it's easy to forget these little kinds of things. Well, any questions, folks, before we go to the next part? Okay, so aside from the central limit theorem, aside from the rehash on the standard error, the other thing we need for hypothesis testing with the population mean is the degrees of freedom. Where you see degrees of freedom written out, the common symbol is df to stand for degrees of freedom. The formula is fantastic. It's n reduced by 1, n minus 1. So all we do for that one is we go to sample size. If you drop in 24, that's completely fine. I'll put it in a paper trail in the notes. It's 25 minus 1. So this problem has 24 degrees of freedom. What this now tells us, here's the new part, is to calculate a p-value, here's where we will go. Use TCDF. So T is standing for the T distribution. CDF is just like normal CDF. This is going to give us areas under the curve. If you're curious what CDF means, it stands for cumulative distribution function. But CDF for short is definitely a great shorthand. So you'd use TCDF. That means you go here in your calculator, hit second vars, go down to this option all the way down below here, TCDF. Looks like it's option 6. I think that's a worthy screenshot. If you enter there, option 6 wants a lower bound, an upper bound, and a degrees of freedom. So very similar to what we did for hypothesis testing with the proportion. But let's put that actually on this notes right here, just for a quick screenshot. So here's TCDF, option 6. Well, any questions, folks, with our kind of a preview review example 1? Okay, the next segment of the notes are pretty tough to look at because it's just like a wall of text. But the goal of it is to go back here, section 15.3, the reasoning for hypothesis testing. And what we want to do is this whole table all over again, just to see how it goes in our new setting and see what the carryover is, the commonalities and the differences. Also, we have to describe our new hypothesis test because this one only works for categorical data with 2 outcomes specifically. So we're using this new procedure the moment you realize these data are quantitative. What would make it quantitative? You might have units, or you might have an average or a standard deviation. That alone tells us we're doing this process here with TCDF. So here's how it goes next. We call this one the one sample t-test for a population mean mu. To use this test, we need 2 things, and pretty much the same step 1 as from before. We need a random sample from the population of interest, or we need the experts who worked really hard on this problem to tell us that the sample is selected in a way that would result in a sample representative of the population. That's the shady statement. We prefer to see that it's a simple random sample. If someone ever gives you that statement there, they have to have pages of documentation of why that ought to be plausibly true. It takes a lot of convincing. Next, condition 2, well, this one just depends on what your data looks like. If you have a large sample size above 30, then you can use the central limit theorem and you can get accurate results using our methods. If you know that the population is distributed normally, then the central limit theorem works perfectly and there's a lot less worry on the sample size. We won't look into condition checking too much in this because it's just an introductory class and we don't have a lot of time. But if you're curious on how it would go, if you're checking conditions on this problem, you take all of your data and then you put it into a histogram and you just look at how skewed is it. If it's really skewed, then we would hope we have more than 15 lakes, at least 30. But if these data are pretty symmetric, then even at a low sample size of 15, it would be acceptable that it met the conditions. But again, we're going to focus less on the conditions because of time constraints, and just because of the simple fact it's an introductory course. We can only do so much with the time we have. So those are the conditions. Fast to go through, look for a random sample, and check how large the sample size is. After we look at the conditions, in the last section, we calculated a z-test statistic. We put in p-hat, that's the statistic. P-naught came from a null hypothesis, so down here. And in this setting, we were allowed to work with the actual standard deviation. It's provided when the null hypothesis is true, but that doesn't happen in our situation. So here's the small changes for us. The standard error has to go in the denominator here. We don't know either value of mu nor sigma. We still assume that the null hypothesis is true, but all that gives us is a value for the mean, mu. It doesn't give us anything for sigma whatsoever, so we still use the standard error. Button above, we have the statistic. We subtract this value mu naught, which comes from the null hypothesis, and that part there is exactly the same. So this is the value to be tested that we have to identify. And all this t-test statistic is trying to do is the following. This measures the number of standard deviations that y bar, that's your actual data, is away from mu naught. This is your research claim about the data, that nothing has changed, the null hypothesis. So t is once again nothing but a z-score, really. It's measuring number of standard deviations. Then we get our p-value coming from the t distribution with degrees of freedom, df equals n minus 1. So all we need to specify then is how we get our p-values, and we're on our way calculating or running through some hypothesis tests. Any questions first, folks, with the information here? Okay, because this is kind of a compare and contrast against section 15.3, categorical data, let's add a couple more things to the notes. One thing we should mention here is if the data is categorical, then the test statistic is z equals p-hat minus p-naught divided by standard deviation of p-hat, where standard deviation of p-hat was this expression, square root p-naught times 1 minus p-naught divided by n. So that's how we got our test statistic in section 15.3. The curious thing about this is if you look at section 15.4, that's an easier process actually. You put in the standard error, it's a faster formula, and well, the numerator is essentially the same in a real sense, statistic minus the hypothesized value. Well, let's take a look at what the p-values will be. Any questions first, folks, with our comparisons? Okay, the p-values, the way we specify them, are very similar to how we specified them in section 15.3, but this is tricky enough to really rehash it. So let's go through these all once again. So if your test is a right-tailed test, your null hypothesis is always going to have equality, but your alternative hypothesis will have a greater than symbol right here. So in the right-tailed test, here's what the p-value would look like in this situation. We draw a curve that kind of looks like a normal curve, but it really isn't. This is a t-distribution. So So we can indicate it by calling it a t n-1 curve. The n-1 is referring to the degrees of freedom in the problem. That's a decent dot to connect, I'd say. The t distribution is centered directly at 0. And our test statistic, which we label as t from up here, well, it could be anywhere. It could be far to the left, far to the right. It could be exactly 0. That'd be kind of amazing. But in a right-tailed test, we'd hope it's somewhere far to the right, over here. So that would be our t test statistic. Coming in next is, let's use, how about, sorry, trying to pick the right colors. Let's go with this one, slight off blue. This region right here is your p-value then in this test. So that'll be your p-value. To actually calculate it, you have to put in t as input 1. So this will be your lower. 2 for upper would be equal to 10 power 99. And input 3 is the degrees of freedom, n-1. And in either case for the p-value, let's just reiterate this here, use t-CDF, like we specified earlier. So those would be the inputs to get your p-value for this situation. If we do the left-tail test, really this whole picture just sort of reflects across 0, but let's write it down anyways. So here's what the look is for a left tail. So this is still the t n-1 curve, still centered at 0. As before, t can still be anywhere. Usually if you're writing out a left tail test, you probably put your test statistic pretty far to the left, but let's emphasize it really could be anywhere. Let's place it right here because that's a legitimate value you could really get on these problems. So let's suppose our t-test statistic landed in that location. Then, because this one is a left-tail test, the area we shade is to the left now. And because we shaded to the left, this tells us what our inputs are going to be for the t-CDF portion of the calculator. This time input 1, which is lower. Anyone see what this one should turn into for this problem?
The lower would it be the t?
Well, the t on this situation would be the upper value. So this one is the input 2 upper.
Yes.
Exactly, yeah, this is going to the left forever. So just as you said, negative 10 power 99 in this case. And this is a decent idea to connect as well. There's so many little things that you might want to highlight. You don't want to make the notes too busy. But if it's a right-tailed test, you'll notice that implies immediately upper is 10 power 99 in a right-tailed test. If it's a left-tailed test, that implies immediately, this time the lower is negative 10 power 99. If it's a two-tailed test, now it's confusing. That's the one we spend more time kind of dissecting. But we have input 1 for lower, input 2, the test statistic for your upper, and input 3 is still degrees of freedom, n-1. So that's what happens in the right-tailed test and in the left-tailed test. And in the two-tailed test, p-values are twice as large as in the other tests. That seems kind of rough because we've said all along the two-tailed test is the default test, and we're also saying it has twice as big as a p-value, and that's not great because we want small p-values to reject the null hypothesis and support the alternative. So why would we ever want a two-tailed test when the p-values are twice as large? Well, it's because this now requires that you have extra information, extra evidence now to reject the null hypothesis and actually support the alternative. And sometimes your hypothesis doesn't even know a direction you're expecting. Sometimes we think things should be larger, sometimes it should be smaller, but if we have no idea, we go for the two-tailed test. Here's where it gets tricky though. In a two-tailed test, the way we compute depends on the sign of your test statistic. Your test statistic t could either be positive or it could be negative. So like before, let's split this into two charts down the middle. This is for t positive on the left and t negative on the right. So let's just draw that out. So here's one t distribution, here's the other. So this is TDF, TDF, again for both. And I wrote that in a slightly different way. Let me put n-1, just for the sake of parallelism. Sorry about that. Degrees of freedom is n-1. Both are centered at 0. But we said on the pane to the left, to the left here, t is positive. So we have to put it to the right. On this pane, we said t is negative, so we have to put it to the left of 0. And in both of these cases, it is a two-tailed test, which means you get your p-value from both of the tails. So that's our p-value in this case. It's kind of annoying because it's spread out into two places. And sure, you could use the lower upper for this one right here. You can go lower upper again with t test statistic being the lower and calculate this one. But you're working twice as hard as you have to. The strategy is find the value here and double this area. We look back on what we did in 15.3. That's what we were trying to specify here. If z is positive in this location, we double whatever the result comes in this value. So let's carry that in and just make it official for these notes. If your test statistic came out here on the two-tailed test, which we'll definitely do one of these on these notes, then this will be your lower. Option 2 for upper is 10 power 99, so positive. Input 3 is just the degrees of freedom, n-1. And the big reminder is double the result from this. If you do that, you've doubled the area right here by the red dot, which is exactly the area to the left over here. And so you've calculated the p-value legitimately with that. Kind of a small hack. Over here, if the test statistic is negative, same idea, but what goes in for lower and upper changes on us. So over here, we would say input 1, lower, is negative 10 power 99. Input 2, upper, would be equal to t, the test statistic. In all of these cases, input 3 is degrees of freedom, n-1. And this time over here, we double this result, which means we're doubling that area right there. And on the other pane, we were doubling that area here. So that's the full procedure, folks. It's kind of annoying that one procedure for a hypothesis test could give you 4 different ways to calculate a p-value. But the good news is there is a ton of parallelism here. If you feel like you're losing your way, look back at what you did in section 15.3, because really the only thing that's really new about all of this is the test statistic right here, is the big change. Well, any questions at all, folks, with running through our p-values? Okay, so what do we do after we calculate the p-value? We make a comparison. A hypothesis test must also come with a level of significance, alpha. It's usually stated in this way. Choose a level of significance, I guess not in this problem. It's usually stated in this way in this problem. Test appropriate hypotheses using a significance level 0.01. So we wrote alpha as 0.01 from that information. And our hope of hopes is that the p-value in this problem is below 0.01. Let's check out how it came in. I don't even remember. It wasn't. So we failed to reject the null hypothesis on this one. which means we said our data does not support the statement in the alternative hypothesis whatsoever. So that's what we do with the p-value next. And this table down below is just a reminder, that's how this all comes into play. Once you get your p-value, you compare it against the chosen significance level alpha. If it's below alpha, we've rejected the null hypothesis, which means we found evidence. The alternative is true, significant statistical evidence. But if it's larger or exactly equal to, same statement, except we failed to find the significant evidence. Let's double underline the failure part. So your conclusions almost look the same, except on the second one, you say we failed to find that evidence. On the first one, you just say we did find that evidence. In either case, the big warning is always, we never make a conclusion that says H naught is true. That's the really unfortunate thing about hypothesis testing. Sometimes the null hypothesis is the statement that people want to say, find evidence for. But you can't do it with this format at all. The thing we're looking for evidence on is always the alternative hypothesis. So that's our big rundown of hypothesis testing from the very start, the central limit theorem, to the finish, making the decision based on your significance level. So what we'll do next immediately is put all of it into play on example 2. Any questions whatsoever, folks, with the full process? Okay, it's a lot to digest, but when you're doing this as a final exam question, it's going to look pretty much just like this. You could almost say at this point, we are reviewing for the final exam, even though this is our first problem. So let's give this a try. We'll zoom up and look at the notes if we have to cite anything, and we'll be sure to put it in a high level of detail. Let's start by absorbing the context. It says the ankle brachial index, we'll say ABI for that, compares blood pressure of a patient's arm to blood pressure of a patient's leg. So you could imagine your arm out here as having a different effect being so close to your heart. They want to compare that against what's going on with your blood pressure down in your leg, further away from your heart. I'm not too sure why, but let's see if they'll tell us. The ABI can be an indicator of different diseases, including arterial diseases. And they say next, a healthy ABI is 0.9 or greater. That sounds like specific information, so let's highlight that. It's not easy for me to say what I could do with that value, so we'll come back to it when we need to. So this is a more interesting context. We're now zeroing in on an actual study that happened. This is a real study done by these folks in the Journal of American Geriatric Society. It was titled Sex Differences in Peripheral Arterial Disease. So we are definitely interested in arterial diseases, it looks like. Let's add that. The researchers obtained the ABI from a random sample of 187 women. So it looks like they're focusing specifically on one gender. Let's say we have N is 187 women with peripheral arterial disease. So again, looks like that's going to be the big part of this problem. This is highlight worthy because this is the sample. It implies what the population is now. The population will be all women with peripheral arterial disease. Too bad we don't have an acronym for that, but I guess that'd be too many acronyms. They go on next to say, the results were a mean ABI of 0.064. That's really good information for us because they gave us a statistic there. Let me get the pens caught up. So that told us Y bar is 0.64. Unit here is ABI, ankle brachial index. It's also a blood pressure, which has its own specific kind of unit. So we'll just refer to it as ABI to simplify. It says also it had a standard deviation of 0.15. But you know, one question for the class is, how in the world do I know these are statistics? For example, maybe that should be mu, and maybe what should be below here, maybe it's not S, maybe it's sigma at 0.15. There really is actually one word starting at this sentence that tells us they're talking about the sample, not parameter values of the population. It's right here when it said the results. They're referring to the results of the random sample. That means these are really describing just the sample. They're true statistics, and we should describe them with Y bar and S. But that's one thing that's also vague about statistics. That's super important, but someone describing a statistical problem to you may not know that, so you have to infer it by everything that's being told to you. They tell us next, we're going to do everything at a 1% significance level. That's a symbol 2. That's the thing we compare a p-value against. From that, we should write out alpha equals 0.01. So that's our significance level. And from here, it goes on to ask, do the data provide significant statistical evidence to conclude that, on average, women with peripheral arterial disease have an unhealthy ABI? That's a question, a specific research question. That's essentially your alternative hypothesis then. So let's give that a special color as well. By the way, if you like color coding, you're welcome to bring highlighters and that kind of stuff to real exams. That's completely fine as well. So this is pretty much a statement of HA. We have to state it in terms of the actual parameter we're testing, but it's good to know where to look. Sometimes that question mark is a dead giveaway. That's a research alternative hypothesis. Okay, so that's the whole context. Any questions or comments so far? Okay, now it goes on to say, describe the unknown parameter. Really, before we jump into it, we should ask ourselves and answer it one question the moment you see this. Is the data categorical or quantitative? Any volunteers for the assessment on that question? Absolutely. It's kind of hard to tell here, to be totally honest, but I don't see any percentages. I don't see any proportions. And these data values, 0.64, they do have a unit. It's units of ABI, ankle brachial index. Yeah, exactly.
They're just talking about one thing, so.
Yeah, no successes, failures, is that what you're referring to? Exactly. That's a great way to think about it as well. So that tells us it is quantitative. Let's say here, if so, use mu. So if your data is quantitative, you're describing a parameter by calling it mu, the population's mean. If it's categorical, then let's say here, if so, use P, the population proportion of successes. So in our problem, as you indicated, it is quantitative, so we're going to be using mu. We'll start off by saying mu equals the population mean. You could say, again, the true mean, population mean. You could say the true average. I like that one because average is easier to understand when you're explaining your results. You could say the population's average, but you do have to say either mean or average somewhere to indicate the type of parameter. So it's going to be the population mean of what? Well, if your data is quantitative, go immediately to your unit. Population mean ABI. So this is the data. We're looking at ABI values. What we have to say next is, of all, this part we're describing is the population. Anyone see what the last part should be in describing the population?
All women with peripheral arterial disease.
Exactly. With,
Have an
yeah, some of them might have a healthy, some of them may have unhealthy, but we're gonna find out what they have on average. So it's gonna be the mean ABI of all, I forgot to say women, let me put that in there. All women with, it's peripheral arterial disease, but you can kind of paraphrase that by saying this arterial disease. That's a really kind of a formatting, stylistic choice, but it's okay to say this arterial disease because we're only talking about one of them in this problem. So there's no ambiguity in saying it like that. And if you're talking to people about this problem, that's probably how you would say it as well. You wouldn't say peripheral arterial disease every single time it came up. You would only really specify that when you're writing up the context. So we have described the unknown parameter. After we do that, we'll move on to the null and alternative hypothesis. But again, I feel like that is the hardest part of the problem. By the way, now that we're doing a hypothesis test, there is one thing that we missed. We have the sample size, significance, y bar and s, but we still don't have mu naught. This is going to be the value. Let's say it's slightly different, the hypothesized value to be tested. And it's somewhere in this problem, but we have to dig it out. Anyone see what mu naught is equal to? It wouldn't be y bar in this one. It's got to be something else given in the problem. Absolutely, good call on that. So 0.9 right here was the hypothesized value. Good call, Tiff. And if you didn't see it, here's a way to kind of think through it. If we're going to write down the null hypothesis, H naught, it goes in like this. Mu equals, and then whatever mu naught is, it goes there. Well, that didn't help me very much, but we can now put down the alternative hypothesis, HA. It goes like this. Mu, because we have to decide on the type of test, whether it's a two-tailed, left-tail, or right-tail test. But mu naught would also go right here in this location. Then what's special about writing down the alternative hypothesis, though, is it brings you up here where it's highlighted in yellow. That's the alternative hypothesis. Do the data provide significant statistical evidence to conclude that on average, women with peripheral arterial disease have an unhealthy ABI? Well, a healthy ABI is at 0.9 or greater. So an unhealthy ABI is in the opposite direction, 0.9 or lower. This is a really tricky problem because the context kind of makes you jump through loops, but it's a pretty honest statistical problem. This is what they look like in the wild. They're a bit of a mess. They do get simplified a bit on the exam just to streamline things, but that's how we get mu naught equals 0.9. It goes then down right here, 0.9. And the null hypothesis is a claim that nothing special is going on, that even women with peripheral arterial disease have a healthy ABI, ankle brachial index. So that's what the null hypothesis is saying. But the alternative hypothesis is asking, do they have an unhealthy ABI? Let's see. Healthy is at 0.9 or greater. So unhealthy is exactly, or lower is now telling us this is a left tail test. So we go and put down
Would it be less than or equal to?
just a strict less than. Yeah. So strictly less than the 0.9. One way to think about these as well is that when it comes to equality, equality only occurs in one spot, just the null hypothesis. We got it, folks, that's where mu naught goes. And this would be considered a full answer, but sometimes people want to add a little bit more to this, and I totally get it. This could be really a nice sentence. You could say, test. H naught mu equals 0.9 against, well, let's say versus, because I didn't leave a lot of space. The alternative hypothesis, mu is less than 0.9 at, here we're writing down the level of significance. This is good to have in one line because you always come back to look on this line. We're testing this at alpha equals 0.01. So we are requiring a huge level of evidence before we support the alternative hypothesis, which makes sense because this is a medical problem. We don't want to make a false positive on accident. So we're making a lot of evidence be the benchmark before we try to make a big claim about this condition, having this arterial disease. Does that look right to folks for hypotheses? Awesome. So once you get to part C, it's kind of like smooth sailing. This was the hard part, parts A and B, breaking down the context. But now we're just writing down formulas. When you see this, degrees of freedom, think the shorthand, DF. Just writing that down might, by muscle memory alone, help you remember it's the formula n-1, which means we go right up here, sample size n, and put in 187 minus 1. So we have 186 degrees of freedom on this problem. By the way, it looks like the conditions would be met. This is a random sample. The sample size is very large. So even if the population is skewed, it doesn't matter. The central limit theorem will give us normality for the sampling distribution of the statistic. But next thing we need is standard error. I think this is a good place to use a little bit more color coding. There's two kinds of standard error. So this is kind of a review question all on its own. So just for the sake of, if it's a different problem, think in these terms. There's two things that can happen. If your data is categorical, your standard error goes SE P hat, and that reminds us it's the formula P hat, 1 minus P hat, divide by N. So that's the standard error for categorical data, and this could only be used for confidence intervals. It can't even be used for hypothesis tests in the first place. You use the actual standard deviation in the hypothesis test. But if your data is quantitative, then when we say standard error, we're referring to standard error of y bar, and the formula is S over root n. Kind of a nice formula. It's kind of weird that we do the categorical first because that formula is kind of nasty to even look at. So our data is quantitative, so that means for us, it's standard error y bar. So now we're calculating it. The formula is take S, divide by the square root of sample size. Let me fix that in, it looked kind of shady. So like before, we're just substituting in values. S is way up here at 0.15. Divide by the square root of 187. And this is a mistake I've made myself. It's kind of embarrassing because it's not easy for me to find this mistake. It's really easy when you say the degrees of freedom is 186 to accidentally put 186 into that denominator, and now your results are off. There could be off enough to tell on a final exam, but you wouldn't lose too much points. But it could be off enough on my stats lab that you can't get the question right, even though everything is done perfectly. So watch out for that weird thing. In either case, we just need to jump it into the calculator. Anyone happen to have a value?
0.01096.
Thank you. 0.01096.
That's 0.0109. Well, it'd be, I don't know, that's 5, so you round it.
It looks like we're rounding to 4 places. This is rounding with carry, my least favorite. So this will become 0.0110. So we'll use that answer there. Does that look right to everyone so far? Okay, so we've got the standard error down. Once you get your standard error, it's time for the test statistic. This is going to measure the number of standard deviations that the actual data Y bar is at 0.64 for ABI, is away from your hypothesized mean at 0.9. Notice it's actually kind of far away, 0.9 to 0.64, because the standard error is tiny. It actually looks like it's a lot of approximate standard deviations away. So let's calculate it officially. It's the t-test statistic. So it'll be t equals y bar, excuse me, minus mu naught divided by the standard error of y bar. So pretty much the way these questions are going to go on the exam is parts A, B, C, D through F. It's really just a step-by-step strategy guide to do a whole complete hypothesis test, taking the usually best steps in the right order, in my opinion, at least. So next thing we're going to plug in, now that we have the standard error, it's a sample mean y bar. I'm getting to the point of the problem where I need to take some screenshots. Let me grab all of this here. So for y bar, we plug in 0.64. Subtract off mu naught at 0.9. That came from right here by the red dot, your null hypothesis. And then finally divide by standard error of y bar. Way over here, 0.0110. So again, this t-test statistic measures the number of standard deviations your data is away from the claim in the null hypothesis. So on this one, it's going to be 0.64 minus 0.9 divided by 0.0110, and we get negative 23.6364 standard deviations.
Wow.
That's like going from the planet Earth to a different star in terms of distance. This is so far away, the calculator is going to struggle to give us a p-value that's not zero at this point. I don't think it can. But that tells us we are assuredly at any significance level alpha rejecting the null hypothesis. So this is one of those problems where the evidence is overwhelming against the null. So we've got negative 23.6364 upon rounding. And for the p-value, let's carefully calculate it out and see what the calculator does for us. Any questions first, folks, with part E? Okay, so once we get our test statistic, we use that to come up with the p-value, but we have to look to that, the alternative hypothesis. It tells us this is a left tail test. Let's just take this whole thing. And because we know this is now a left tail test, because of that less than sign right here, here's what the picture looks like now. So this is the T, and we put in the degrees of freedom right under it. This is the T186 distribution, centered directly at 0. And our test statistic, this value, I can't put it on the plot in a reasonable way, so I'll just sort of go like this, plug it into here to just kind of convey it's really far that way. You can't really put it on paper accurately. But still, it's a good visual for actually getting out the information you need from the calculator. So that's a t-test statistic at negative 23.6364. Our p-value goes this way because it's a left tail test. Let's put in those same inputs as before. Input 1, lower, is negative 10 power 99. This is input 2, the negative 23. 186 here is input 3, degrees of freedom. And for this whole process, we use TCDF. So we're trying to get that area, but it's a lot smaller than we think. But keep in mind the weird thing about this curve. This curve that we're describing never even touches the x-axis, no matter how far you go to the left. There is always area, but it approaches the x-axis so rapidly, our calculator might have trouble finding it. So let's give this a try. Hit second vars, go down to option 6, going way down there, TCDF. Enter on that one. This is our calculator's way of saying negative 10 power 99. So you could leave it like that if you have this put in, but it's not very helpful for folks typing this in. Let's type it in the way we typically would. Go negative 10, up arrow to put in the exponent, and 99. Next is our test statistic. So negative 23.6364. You have to give it a degrees of freedom. And in this problem, it's the 186 we calculated. And this should do our computation for us. So enter a bunch of times. And it is a 0. It's not quite 0, but what it's telling us is that the scientific notation to give you the real number goes beyond negative 10 power 99. The calculator is a finite machine. Its order of magnitudes don't go far enough to even show you this number in scientific notation. What we would say in this case is, oh dear, let me control Z that, sorry, hit enter in the wrong spot apparently. What we would say in this case is the p-value is approximately 0. So this can happen in a real homework problem, and it makes these instructions kind of weird. If you're going to round to 4 decimal places, well, you could put that in. It seems silly, honestly, but that could work as an input. I think my stats lab is smart enough to actually just take the 0 though and know that's equivalent to 0.0000. But just a further investigation on this calculator, what if it wasn't negative 23? Let's put in a different number. Let me go second vars, TCDF. Let's say it was negative 5 standard deviations instead. That's still fantastically far away from 0. To enter on all of this. And at negative 5 standard deviations, this is what you would get. 6.59 times 10 to the power of negative 7, which means this decimal point goes to the left 7 spaces. So 0.00000006 and some change. And that's at a negative 5. So that tells us at negative 23, our calculator really had no choice or no chance of giving us a value. But that's okay because whatever we got is assuredly less than 0.01. So the answer is the p-value. But this is a good step to put in a little bit more. That p-value is less than 0.01, which is alpha. And so we will reject H0. That means we're ready to finalize the rest of the work on this problem, the practical conclusion. Any questions at all, folks, with the weird p-value this time? Okay, the conclusion we give is exactly the same kind of conclusion we would give right here. We go up to the hypotheses. The screenshot I want to take is also going to grab the parameter mu. So when it says we reject H0, visually, that's what it looks like. It's gone. And we're supporting that statement right here. So here's how our conclusion will go. We have found significant. Let me actually rephrase that. When your p-value is that small, it's an appropriate time to now say words like these. We have found overwhelming evidence, let me say statistical evidence, in support of the claim that, now we come over here, and right where the alternative hypothesis statement is, we're reading this out verbatim using ordinary words, no symbols. So we'll place a mu just right in what you said earlier. We have overwhelming evidence in support of the claim that the population mean ABI of all women, it's peripheral arterial disease, but we'll just say this arterial disease with this arterial disease. Now we come over here and we'll say has or is less than 0.9. The statement's pretty much over here, but just as a reminder, this is telling us which is in the unhealthy range, which was their larger question. Do they have a healthy or unhealthy ABI? They were asking for specifically the unhealthy one. That's why we had a less than there. Well, that's how the conclusion would go in that state for that statement. Any questions so far, folks, with our last part here? Okay, so that's hypothesis testing in a nutshell. Example one was meant to be kind of an easier one. This one was a left tail test. When we come back on Wednesday, we'll do the harder one, which is the two tail test. And it doesn't even provide us with any statistics, so I think we have to calculate all that stuff from scratch. But this will be a pretty good review problem on its own. After that, we'll just be doing generic review questions, reviewing for the final exam. So any last questions or comments, folks, for where we're at so far? Okay, well, this is the last type of problem that we're doing in the course, so congratulations, everyone. Oh, sorry, Carly, I did miss your question like 6 minutes ago. Sorry about that. Oh, yeah, so to put in that -10, it goes like this. Let me go back to the menu where we were doing that. So inverse T, or, well, this will be a good one to do it in anyways. To get the negative, you would use, hang on, let me get to the right spot. It just looks weird. TCDF, there we go. So to get the negative, you have to use this negative sign right down below right here. And it's really frustrating because if you use a subtraction sign, it'll say syntax error. So use that negative, just kitty corner bottom left from the enter, then 10, and this up arrow gives you the exponent, 99. Does that make sense, Carly, on getting that in? Okay, well, that's pretty much all I have for folks today. We'll come back on Wednesday's class and work through the second exam and then start reviewing. Also, glad to hear that, Carly. We'll take care, folks. If you do have questions, I'll be happy to help out. Otherwise, I'll see you all in Wednesday's class.